In order to do transformations, the first thing you need to know are your parent functions. So the first parent function is the quadratic function, which is f of x is equal to x squared. Some numbers that can help represent this function would be when x equals 0, -1, -2, 1, and 2. When x equals 0, y equals 0. When you put 0 in for x, 0 squared is 0. If we put -1 in, -1 squared is 1. -2 squared is 4. 1 squared is 1. 2 squared is 4. Now let's plot these points. So we have 0, 1, 1, -1, 1, 2, 4, -2, 4, and 2, 4. And so here's our parent function. So the domain is where all the possible x values that this function touches. It can touch any x value from the right and the left, so that means that domain is all real numbers. The range is all the y possible values. We only see y values up here. It's not possible to have any y values down here. So what our range is going to be is y is greater than or equal to 0. Or another way you could have written this is like this. Now let's look at the next parent function. So f of x is equal to x cubed. Some numbers that can help figure out what this function looks like are 0, -1, -2, 1, and 2. We put -2 in for x cubed, we get -8. Put -1 in for x cubed, we get +1. Put 0 in for x cubed, we get 0. Put 1 in for x cubed, we get 1. We put 2 in for x cubed, we get 8. This should be negative right here as well. So when we plot these points, we have 0, 0, 1, 1, -1, 1, -2, 2, 3, 4. About right there. About right there. And so we have a function that looks something like this. Our domain, there's no possible x value that is not able to be touched on this, so that means it's all real numbers, and our range is as well. Next parent function, we have the square root function. So we know whenever we have a negative underneath a square root, we get undefined. So some numbers that are going to help us out with this are 0, 1, and we want to choose numbers that are going to be a perfect square root under here. So for example, when you put 1 in for x, you get as your y value 1. But if you were to put 2 in for x, you would get square root of 2, which we know isn't a nice number to look at. So let's choose our numbers carefully. 3 is not going to give us a nice number, but 4, square root of 4 is equal to 2. So let's use that as our x. So when we put these numbers in for x, we get for 0, 0, 1, 1, and for 4 we get 2. When we plot these numbers, we plot 0, 0, 1, 1, 4, 2, and we get a function that looks something like that. Our domain, it's not possible to have any x values over here because, like we said, if you have a negative underneath a radical, you're going to get undefined. So that would mean that our domain is x is greater than or equal to 0, or this could be written like this. And our range, you can see here that there's no negative y values. So that means our range is also going to be y is greater than 0 or equal to 0, which can also be written like this. Now let's look at our next parent function, the cube root function. So unlike the square root function, you can have negatives underneath this radical, and the reason behind this is because it's an odd root. For example, if you have -1 times -1, we know that's going to give you a positive number of 1, which is why a negative is undefined here. However, if you do -1 times -1 times -1, that makes the answer, again, -1, which is a negative number, which is why it's able to work for a cube root function. So, some numbers that can help find our function here are 0, -1, 1, and just as before, we need to be careful choosing our numbers because we want to choose numbers that are going to be easy for us to graph. So the next number that we're going to want to choose is -8 and 8. When we put -8 underneath here, we get negative we get negative 2. When we put negative 1 in for here, we get negative 1. We put 0 in, we get 0. Put 1 in, we get 1. We put 8 in, we get 2. Now let's graph these points. This point is off the graph, which is okay, but we know it's over here. Negative 1, 0, 1. And we know these points are off the graph. They look something like this. Our domain is going to be all real numbers, and our range is also going to be all real numbers. Now let's look at the next parent function. So our next parent function is the reciprocal function. We know that when we get a 0 in our denominator, we get something that's undefined. So we know 0 is undefined. But any other value we put in our denominator is going to give us a defined number. So some numbers that we can plot are negative 1, negative 2, 1, and 2. When we put 1 in for our function, we get 1. We put 2 in for our function, we get 1/2. When we put negative 1 in for our function, we get negative 1. Put negative 2 in for our function, we get negative 1/2. We're going to have asymptotes at y equals 0 and x equals 0. And then we're going to plot our points, and we're going to get a function that looks something like this. Our domain is x does not equal 0. It equals all real numbers besides x does not equal 0. And our range is y does not equal 0. And it equals all real numbers that are not 0. Our next function is the absolute value function. So what this function does is it turns whatever value our x is and it makes it positive. So some numbers we can plot are 0, negative 1, negative 2, 1, and 2. This would make this 2, 1, 0, 1, 2. And when we plot this function, we get something that looks like this. Our domain is all real numbers, and our range is y is greater than or equal to 0. Now let's move on to the greatest integer function. So what the greatest integer function does is no matter what the number is, it rounds that number down to the greatest integer. So what I mean by that is here, we have 4.2. We're going to round this down to 4, and that's our answer. We round down no matter what. Even if it's 4.9, we still round down to 4. That's what the greatest integer function does. Here, it's equal to 5. That's the greatest integer. It's just 5. 3/8, we would round down to 0. Negative number, trick question. This would round down to negative 1. This is about 1 point and then a bunch of numbers, so this is going to round down to 1. And pi, which we know is 3.14, would round down to 3. So now, when we graph our greatest integer function, we can add any number here. So, some numbers that I have in my graph, I put negative 2, negative 1.5, negative 0.8, 0, 1, 1.4, 2.2, 3.1. You could put any number you want. These are the numbers I chose. So, round this down, negative 2. Round this down, also negative 2. Round this down, negative 1. Round this down, 0. Round this down, 1. Round this down, 1. Round this down, 2. Round this down, 3. The way this function is graphed, if you think about it, say we have 0.5. We know it always rounds down. So, when it's 0, we know it just stays 0. When it's 0.5, it rounds down. When it's anything up until 1, it is going to round down to 0. Same thing here. So what this function ends up looking like is this. Closed circle, open circle. Closed circle, open circle. Closed circle, open circle. Like this, and so on, and goes on forever. So what our domain is all real numbers, and our range is all integers. Okay? It doesn't touch anything in between. It can't touch here, which is why the range is only integers. The range could only be, the y value could only be integers, while the domain could be anything. Now let's go on to our shifts. When we see something being added at the end of the function, that means it's shifting our function up. When we see something being subtracted at the end of our function, it's just shifting our function down. When we see something being added on the inside near the x, x's are weird, they do the opposite. So even though it's plus, we are going to move it to the left. Anything associated with the x does the opposite. Here, this moves to the right. When we see a negative on the outside of the function, this is affecting our y's. So if our y's are flipping, then our y's are flipping over the x-axis. So when we're flipping over the x-axis for this. Here, this is affecting our x's. When our x's are changing, we're flipping over the y. So flip over y. When you have a c that's being multiplied by an entire function, you're multiplying all of your y's by that c. So multiply and when you see a c on the inside of a function being multiplied by all the x's, you are going to multiply the x's by 1 over c. Now that we've gone over all of our transformations, let's give it a try. So, first problem. We see we have a minus 3 on the inside and we have a plus 2 on the outside. This is going to shift our function to the right. This is going to shift our function up. So, we know our original function looks something like this. There's our original function. That's our original function, and we are shifting this to the 3 to the right and 2 up. This is where our function is going to end up. 3 to the right, 2 up. And here is our final answer. Our domain is going to be all real numbers, and our range, we have a new range now. So since we moved 2 up, we can see that our y is going to be greater than or equal to 2. Let's move on to the next one. So the next one, we can see here, our original function looks something like this. Now, what we're going to be doing is we're going to be multiplying all of our x's by 1 over c, which is, in this case, our c is 2. So we're going to be multiplying all of our x's by 1/2. So, here, we have x equals 0. 0 times 1/2 is 0, so it stays the same. Here, we have x equals 1 times 1/2 brings us here. We keep our y the same. There's our new point. Here, x equals negative 1. Multiplied by 1/2 brings us negative 1/2. There's our point there. And so our new function looks something like this. Notice our function is now steeper. Our domain, still all real numbers, and our range, still all real numbers. That hasn't changed. Now let's look at the next function. So, here we have a 2 on the outside. So, since we have a 2 on the outside, we are going to be multiplying all of our y's by 2. So, our original function starts at 0, 0, 1, 1, 4, 2, and it looks something like that. Now, we want to be multiplying all of our y's by 2. So, what we do, we have point 0, 0. 0 times 2 is 0, so that stays the same. We have point 1, 1. 1 times 2 is 2, so we change our y to be 2. So it moves up here. Here we have 0.42. We multiply our y by 2, so 2 times 2 is 4, and we move our point up here. And there's our new function. Our domain is still x is greater than or equal to 0. And our y is still y is greater than or equal to 0. Next function. It's a rational function. So we know this originally looks something like this. It has an asymptote at x equals 0 and y equals 0. So, now, with these types of functions, we are essentially just going to be taking where this is shifting to the right and left, and that is going to be our new asymptotes. So, since we're going to be shifting to the left by 4, 1, 2, 3, 4, new asymptote. Since we're going to be moving down by 3, new asymptote, and that's what our new function is centered around. We have 0.11, so it looks something like this. And here's our new function. Our domain is going to be x does not equal -4. Our range is y does not equal -3. Now let's move on to the next one. Our greatest integer function. So we need to think about this for a little bit. Say we have x equals 1. Now, 1 times 1/2 is 1/2. So now we have x. Now we have as our final answer 1/2. So 1/2 obviously would round down to 0. So that means 1 now rounds down to 0 as well. Say we have 1.5. 1.5 times 1/2 is 0.75, which also rounds down to 0. So now, since we have 1/2 here, that just means that our lines get extended to 2 boxes instead of 1. And we follow on with the rest of our graph. So our domain is all real numbers, and our range is just as before, is only integers. Now let's look at the next problem. So just as before, we need to think about this for a little bit. So if we're at 0, 0 rounds down to 0, and 0 multiplied by -3 is 0. So we know we have a point here. If we look at point 1, 1 rounds down to 1 times -3 is -3. So we know we have a point there. Now let's look in between these points. 0.5 rounds down to 0. 0 times -3 is 0, which tells us that we're going to have something that looks like this. Follow the pattern, and this is what we get. Our domain is all real numbers, and our range is any integer that is divisible by 3, which is that is how we write that. Now let's move on to the next problem. So this problem has a couple things going on. We know our original function. Our original cube root function looks something like this. Now, we're being asked to transform this function by multiplying all the y's by -4 and then moving everything to the right by 1. Whenever we transform things that have multiple transformations, we always have to start with the multiplying every single time. So let's start with that. 0 times -4 is 0. Move it to the right 1. And there's our new point. Now let's look at point 1, 1 times -4 is -4. Move to the right 1. Now let's look at this point. -1 times -4 is +4. Move to the right 1. And we have a new function that looks something like this. Our domain, just as before, is all real numbers, and so is our range. Now let's look at the next problem. So here we also have a couple transformations going on. We know our absolute value function looks something like this originally. So now we need to transform this function. So let's start with point 0, 0. We need to multiply all the y's by negative 2/3. So 0 times negative 2/3 is 0. And now we have to move this to the left 1 and up 4. And we're left with a point right there. Now let's look at this point right here, 1, 1. 1 times negative 2/3 is negative 2/3, about there, roughly. Move to the left 1, up 4, 1, 2, 3, 4. We're going to get something that looks about there. Let's go skip ahead to our point 3, 3. 3 times negative 2/3 is negative 2. Move it to the left 1 and up 4. We have a point there. Let's look at negative 3, 3. So, negative 3, 3. So 3 times negative 2/3 is going to give us negative 2. Left 1, up 4. We're going to have a function that looks something like this. The reason why I skipped ahead is because I wanted to choose a number that would be easier to work with. Our range is going to be y is less than or equal to 1, 2, 3, 4. And our domain, just as before, is all real numbers. So in this case, our range changed a little bit. Now let's look at the next problem. We know this original function looks like this. We have a point 0, 0, 1, 1, 4, 2, and it looks something like this. What we have to do first is multiply all of our y values by 3. So at 0, 0, 0 times 3 is 0, and now the 2 is telling us move it to the left 2. There's our function. Next, 1, 1. Y multiplied by 3, 1 times 3 is 3. Move it to the left 2. There's our new point. Next, 2 times 3 is 6. 3, 4, 5, 6. Move it to the left 2. There's our new point. And there's our new function. Our domain has changed a little bit. Our domain is now x is greater than or equal to negative 2. And our range is y is greater than or equal to 0. Now let's look at the next function. Now let's look at our next function. So we have the function here, 5 minus x in parentheses cubed. So first thing that we're going to want to do is rewrite this function and make it a little bit easier to look at. So what we're going to do is we're going to take out the negative and we're going to make this x minus 5 cubed. So what this negative right here is going to be doing is going to be flipping over the y-axis. So we know our original function looks like this. Now, the first thing we're going to want to do to everything is flip it over the y-axis. It is in the same order as multiplying things because it's on the outside there. So the first thing we're going to do, 0 can't be flipped over any axis. It's already on the axis. And now we're going to want to move it to the right 5. So 1, 2, 3, 4, 5. We have a point right here. Now let's look at this point. First thing, flip it over the y-axis. Flip, move it to the right 5. 1, 2, 3, 4, 5. Now this point. First, flip, now move it over 5. 1, 2, 3, 4, 5. Our new function is going to look something like this. Our domain is still all real numbers, and our range is still all real numbers. And now let's look at our last and final function. Now, for this final function, the first thing that we're going to want to do is change this to make this easier to look at. So, we're going to change this to look like cube root of negative. We're going to take out our negative to make this x plus 4. Now, what this negative does is it flips over the y-axis. We know our original function looks something like this. So now, we're going to use this to find our final function. We look at our point, 0, 0. We can't flip over any axis, so we leave it, and now we move it to the left 4. 1, 2, 3, 4. This point, flip over the y-axis, move to the left 4. 1, 2, 3, 4. This point, flip over the y-axis, move to the left 4. 1, 2, 3, 4. Our new function is going to look something like this. Our domain, still going to be all real numbers. Range, still all real numbers.